Welcome, and for the first session, we are going to have an introduction to our reverse physics approach. But before that, we are going to give you an introduction to the assumptions of physics projects, in case you do not know what it is and what it says. So the main goal of the project is essentially to identify a handful of physical starting points from which the basic laws can be rigorously rederived. You might have noticed, if you studied physics, that the good old theories started with laws of mechanics, laws of thermodynamics, of physical principles in special relativity, and then modern physics started becoming more and more mathematical, where we just say that we have things like Lagrangians, things like Hilbert spaces, and we don't know where they're coming from. And I think that basically that makes the whole understanding of the physics opaque. So what we want to do is essentially go back to the good old days in which we have physical premises as the starting point, so that we know exactly what our theories are about. So one of the things that we want to be able to say, for example, that the assumption of infinitesimal reducibility recovers the classical state. That is, you can imagine to have a ball, you can throw the ball and study the motion of the ball, or you can take a red marker and make a red dot on the ball and throw the ball and study the motion of the red dot. And so the ball, we can say that it's reducible in the sense that studying the whole of the ball is equivalent to studying all the possible red dots that we could put on the ball. And it's infinitesimal reducible if those dots can be made arbitrarily small. Now, the idea is that with this assumption and a couple of others, you are going to recover the classical mechanics. So the classical state really has bundled in this idea of infinitesimal reducibility. On the other side, we can say that the system is irreducible. So, for example, we have an electron and we can produce the electron, scatter them, study the electron, but we can't take a red marker and make a red dot on the electron and then study only what the red dot is doing, because the idea is that when we're interacting with the electron, we interact either with the full electron or none of the electron. And this inaccessibility about the internal of the system makes it a quantum system. This is the assumption of irreducibility. And so the idea is that we want to recover the Hilbert spaces and quantum mechanics based on that assumption. So those are basically the thing that we'd like to say at a high level. And then, of course, the issue is that if you really want to do it properly and understand exactly how everything works, you have to do it at the level of the mathematics and also the most fundamental level of the mathematics, because if you don't know what the lower level of the mathematics are saying, you can't know completely what the upper level of the mathematics are saying. And so we want to be able to say something. If science is evidence-based, then a scientific theory must be characterized by experimentally verifiable statements that have a test associated with them. And then we want to show that under very minimal assumption on these logic of experimentally verifiable statement, you recover topologies in single algebra, which are the more fundamental layer of the mathematics that we use in physics. So that's kind of the idea, and then we have to go through all the stack and do everything. So what happens, and it should be clear by now, is that we don't follow the standard approach that people have in the foundations of physics. Typically, the standard view in the foundation of physics is that the goal of physics is to find the true law of the universe, what actually happens, and what are the fundamental constituents, and sort of how the universe works. And so the goal of physics is to find this theory of everything that explains all the forces, that tells you exactly what are the pieces, that gives you some kind of ontology, that gives you the perfect description of the universe, and it's going to solve all these problems that we have in the foundation, right? And there is a sense also on the people that work on these theories that's the real physics, that's a real stuff that we actually do, and everything else is kind of an approximation and it's sort of some lesser physics. And we don't subscribe at all to this. So if you are looking for a theory of everything from us, so that you're going to be severely disappointed. because we have this different perspective because of what we have found. So we have found that, again, experimental verifiability recovers the mathematical notions of topologies and signal algebra, that geometrical structures are equivalent to entropic structures, as we will see, that Hamiltonian dilution is equivalent to assuming that the system is deterministic and reversible, that it's isolated, and that it's described by independent degrees of freedom. And if you add this kinematic equivalence assumption that we'll see later, you also recover the massive, that you're studying massive particles at and potential forces. So the idea is that from this experience, we saw that it's really the physical requirements and the assumptions that drive most of the theoretical apparatus. So it is what we put in the theory that we find in the theory. And so this kind of contradict, or it's at odds with the idea that these theories are describing the true law of the universe, and that's what we are going to do. Because the productive view for us is to say that physics gives us a bunch of models, different models that can be empirically tested, and therefore for us is just the goal, the true goal that we have is to clarify under what assumption and what conditions those models actually are going to work and give the correct prediction. And so this is our view for the foundation of physics, that essentially we have to construct a theory of physical models, and then every theory is that we have, classical mechanics, quantum mechanics, thermodynamics, field theory, is just a different physical model that you're going to use in different cases. But all physical models are going to have something in common. Like all physical models are going to talk about experimental verifiability. They're going to talk about states and processes and so on. And so the idea is to construct a general mathematical framework in which those things can be well defined, and the tools are the same for all theories. Like in mathematics, you use set theory, and you use set theory regardless of whether you're doing algebraic topology, or, well, maybe you use category theory. But anyway, there is a substrate of things that are common for all the mathematical theories that you're using, and then you go and specialize. So maybe you have sets, and you have topologies that are topological spaces that are sets with added properties. You have groups that are sets with other properties, and then you can have topological groups that sort of put the things together. So we want to have a structure like that for physics as well. We want to have a general theory where there are states, there are experimental tests, and so on. And then you add specific assumptions, and with the specific assumptions, you are going to recover classical mechanics, quantum mechanics, and thermodynamics, so that you can truly understand how these things work and what they're described. So that's basically the overall idea. And how do we do that? Well, we have developed, let's say, two techniques, two approaches to be able to reach this goal. The first we call reverse physics, because it kind of rhymes with the approach in the foundation of mathematics, which is called reverse mathematics. In the foundation of mathematics, we have this approach that instead of taking a theorem and sort of going forward and understanding what can you prove from a set of definitions, you basically go backwards and you find the smallest set of axioms that you need to sort of define and prove the theorems, and that basically gives you an insight on the structure of mathematics itself. And so what we want to do is essentially start from a physical theory, as they are described right now, typically with mathematical tools, and instead of going and making predictions and finding things like, for example, in quantum mechanics, a lot of people try to understand quantum mechanics by looking at entangled system and its special cases. Instead, we will want to go backwards. We want to go and find our smallest set of assumptions required to really derive the theory. So that's one of the approaches. It's an approach that sort of comes from the top, from the theory, and goes down. And then we have another approach, which is called physical mathematics, that is bottom up. You start from scratch and rederive all the mathematical structure from the physical requirement. Again, the idea is not to just set any type of math without knowing what it is. We want to start from the physics that says these are the things that we're describing physically. Then we are going to come out with some physical requirements based on that idea of what we're trying to model. That means that we already have a semantics that is very clear because we know from the start what is it that we are trying to describe. And then we take these requirements and we turn in an encoding in mathematical frameworks. And that's what we call physical mathematics. It's mathematics because it's going to be real mathematics like mathematicians would like to see it, but it's justified for the physics, and it's mathematics that is sort of developed from scratch to know that it is physically meaningful and physically relevant. So for the purpose of this section, we are going to look at reverse physics, and I just want to give you a sort of a sense of how this reverse physics approach, so that you sort of can have some type of general idea. And the general idea, I think it's just better to see it done, and so that you can sort of get a sense. So first of all, we can see a set of results that we have for classical Hamiltonian mechanics. So as I said before, we need assumptions, and one of the assumptions here is the assumption of determinism reversibility, that the system undergoes deterministic reversible evolution, meaning that if I specify the state of the system at a particular time, then I can tell you what its future is and what its past is, right? So that's telling you what's happening now. I'm telling you also what happened before and what's happened after. And what, under this assumption, we are going to have states, and we're going to have some evolution of that state that is given by a displacement field. So at every point, we are going to know in the infinitesimal time step where are we going to go. And assuming deterministic reversibility is equivalent to say that the displacement field is divergenceless, meaning that if we take an infinitesimal region, as many states are going to go in and as many states that are go out. So no state sort of disappears or appears during going through evolution. What happens is that this is just one way to specify this assumption, and there are 8 equivalent ways. So this is one of the things that we like in reverse physics. Is not just seeing things in a particular perspective. So there are a lot of people that like information theory, and then they want to turn all of physics in some sort of information theoretic theory. And we don't want to do that. We say that information theory is going to be important. For example, determinism reversibility is equivalent to conservation of information entropy. But we don't just want to have that perspective. We want to have a perspective from statistics, for example, that the evolution conserves the uncertainty of peak distribution. If you have a distribution that it's very peaked and it goes around in phase space, then the uncertainty of that is going to be conserved. Or we want to be able to say that the evolution is thermodynamically reversible. And again, we're going to see that this is equivalent to the reversibility in terms of maps and conservation of number state back and forth. So it's very important for us that we have as many insights that are equivalent as possible, because it allows us to understand deeper what the theory is describing and have a better understanding of what's going on. So this is one assumption, the assumption of deterministic and reversible evolution. And then we also have the assumption of the system is describable by independent degrees of freedom, which means that the variable that describe the state can be divided into groups that have independent definition, units, and count of state. And again, this same assumptions can be implemented in different ways, can be implemented in terms of information theory. Again, the system allows information independent distribution over each degree of freedom, can be implemented through statistics. The system allows statistical independent distribution for each degree of freedom. And again, the idea is that you can sort of mix and match any of these assumptions from one side and from the other side. And if you pick one on one side and one on the other side, you are able to recover this mathematical formulation in terms of symplectic structure, Poisson brackets, or the curl of a rotated displacement field as a lowercase. And then you can find that these are equivalent to, this mathematical formulation are equivalent to Hamiltonian mechanics. And so now the same equation that you might start and are given to you when you study physics that are very cryptic, now you have the combinatorics of 4 times 8 ways of looking at them plus these other 3. And what happens is that when you're studying a physics problem or you want to get intuition, you can use the hat that mostly that is most useful for understanding that problem. And so this is what we are going to do. We are going to ask a question. We have in quantum mechanics this idea of an uncertainty principle, and one of the things that comes out of reverse physics that it's really very productive to not just look at one theory, but look at the collective of theories in physics and try to understand what is different and what is the same. And so the question is the uncertainty principle really a feature of quantum mechanics alone, or can we find something that is similar in classical mechanics as well? And so we go back to our set of equivalence assumption. We're talking about uncertainties, and we have seen here that there is this condition that the evolution of conserves the uncertainty of peak distribution is equivalent to this assumption of determinism and reversibility. Okay, so what does that mean? How does that work? So the way that you can describe uncertainty for a single degree of freedom in a phase space is through the use of the covariance matrix. So the covariance matrix is essentially a set of expectation, and the covariance between two variables is the expectation of the product of each variables minus their expectation value. So it's the product of how far they are from their corresponding expectation values. And if the values are the same, so this would be position and position, what you get is just the variance. And so this is going to be the variance for momentum. And if the two variables are different, you get what is called the covariance. And the covariance of QP is the same as the covariance of PQ. So this is a symmetric matrix. Like it's everything that is off diagonal, it's going to be symmetric with the transport. And now, of course, a good coordinate-independent way to characterize this uncertainty is through the product, through the determinant. And so the determinant is just the product of sigma q squared, sigma p squared, minus the square of the covariance. And we can call that sigma squared. Now, if the distribution is peaked, meaning that the area that this covariance matrix that corresponds to this is very small, then you can assume that the flow is linear, that your distribution is linear, is moving through seeing a linear field. And then in that case, then the covariance matrix transforms linearly with a Jacobian on both sides. So you have the covariance matrix at time t0, you have the Jacobian on both sides, and that's going to be the new covariance matrix. And so you have this relationship between sigma p, q sigma p minus the covariance and the original uncertainty. And you can see that this, and this is going to be the original one. So it's the same for the whole evolution. So this kind of tells us that there is some type of boundness of the uncertainty, because if we have this original uncertainty, the covariance can only be positive. And so this number, the sigma q sigma p, can only be greater or equal than the product of the covariances that are in the original. Okay, so this is kind of like an uncertainty principle, because we have an uncertainty and there is a lower bound on the uncertainty, but it's very different from the one that we have in quantum mechanics, because this sort of depends on the initial conditions. And so can we do something better? And the idea, well, we can go back and see all the things that we had before and find something else that might be useful. And we have this in terms of the information entropy. The evolution conserves the information entropy. So why don't we go and look at a little bit at that and see what we can figure out. So the first problem that we have with information entropy is that this is the formula is minus the integral of minus rho log rho. And this rho is a probability density. So it has units of probability, which is dimensionless, over units of phase space. And we cannot take a logarithm of quantities that have units. That doesn't make any sense. And in physics, a lot of the time when we have this problem, we just bury our head in the sand and we just go forward. And the point of reverse physics is saying, no, we have to fix all these issues of units, because if we don't fix them, we're never going to have a chance to actually understand what's going on physically. So let's go and try to fix this problem of the logarithm. How do we do it? Well, in principle, we need to multiply this rho by a constant. And this constant is going to have units of areas in phase space because it has to sort of counteract the density of rho. So what does this H mean physically? Well, suppose that you have an area of phase space that is H, and you take a uniform distribution. A uniform distribution will be the inverse of the volume, 1 over H. And if you take 1 over H, put it here, you're going to have logarithm of 1. Logarithm of 1 is 0. So it means that a uniform distribution of an area of H has 0 entropy. And so we have now a good physical representation for this constant. We say that H represents the volume of phase space that corresponds to the 0 entropy for a uniform distribution. And we introduce this constant without knowing that there is a quantum mechanics, without knowing anything. It's just the constant that sets the scale for 0 entropy in classical mechanics. That's it. Okay? So what can we do with this? Well, what we want to do now is to plot the entropy against the uncertainty. So we have fixed our units. And what we want to do now is to have a graph where we put the uncertainty on this axis and the entropy on the other axis. And what happens is that the Gaussian states maximize the entropy for a given uncertainty. So if you pick an uncertainty, let's say 5, and you go up in entropy, at some point you're going to hit a Gaussian, and that Gaussian will have the maximum of the entropy for the given uncertainty. So what happens is that all these region is excluded. There's not going to be any distribution here. There are going to be Gaussian distribution on the red line, and all the other distribution are going to be below. And again, if you look at this, this again kind of looks like an uncertainty principle. We have a sigma q, sigma p on this side, and that has to be greater of something else. So what we can do is take the exponential on both sides, and we get the sigma q, sigma p is greater or equal to h over 2 pi e over e exponential of the entropy. And we have an h over 2 pi, so let's call that an h bar. And now we know that the product of the uncertainties, the product of standard deviations, have to be greater or equal to h bar over e times the exponential of the entropy. And so the Hamiltonian evolution conserves the entropy. And so now we have, we see that entropy puts a lower bound on the uncertainty. And now this is not just a property of the initial condition, it's really a property of the state, because the entropy is a property of the state. So given a state, you are going to have to satisfy those bounds. So it's a little bit better than we had before, because there is no time correlation. Like we're not looking at some initial time, we just look at every time this has to be true. But again, it's slightly different than an uncertainty principle that we have in quantum mechanics, because in quantum mechanics, we just have a constant. There is no dependence on the state. So we need something that bounds the entropy for all states. So we're looking for some other principle, some other idea that says, okay, there is a lower bound on the entropy, and this is the maximum that you can do. And if you think about a couple of minutes, there is such thing already in physics, and it's called the third law of thermodynamics. There are many different formulations of the third law, but one of them is that there is an absolute zero of entropy that is reachable only at a zero temperature for a perfectly crystalline substance, where basically nothing is moving in some sense anymore. So if we now take the third law of thermodynamics and combine it with the entropic conservation that we had before, then we do have a lower limit, and we just take the exponential of the entropy. The minimum entropy is 0, so the exponential of 0 is going to be 1, and therefore now sigma q, sigma p, the product sigma 2 sigma p has to be greater or equal than h bar over e. And we call this the classical uncertainty principle. And again, you can see here in the graph what happens. We have all these region that is excluded by the Gaussian bound. There is all this region that is excluded by the third law of thermodynamics. So the best we can do in terms of entropy of uncertainty is this point here, which happens to be a Gaussian state. And so what we have then is that if you compare the two theory now, they look very similar. They both have an uncertainty principle. Quantum one is h bar over 2, while the classical one is h bar over e. And what happens in quantum mechanics is that you already have the fact that you are following the third law of thermodynamics, because in quantum mechanics, a pure state have zero entropy, and you cannot go below. So quantum mechanics is already incorporating the third law, while classical mechanics is not. That's sort of a difference that it's clearly there. But then what you can see here is that this, the blue one is the plot for the classical bound for the Gaussian bound, and the quantum one is this red one. And you can see that they already become very, very similar, even when you are in this range, right? So that basically what happens is that these two constants are actually going to be the same, such that when you go at high entropy, which high entropy here even just means a couple of units, this Gaussian band is actually the same for both theories. So there is sort of a better reason to way to understand the principle both in classical mechanics and quantum mechanics and quantum mechanics as a bound coming from the entropy. It's the lower bound on the entropy that drives the bound on the uncertainty. And we can even be sure that that's the case in quantum mechanics, because this exponential of the entropy actually is a very important quantity that's called entropic volume. And there is a stronger inequality that you can find in terms of the entropic volume. A stronger inequality means that if you assume this inequality, you are going to be able to derive the other inequality, but it's not going to be the other way around. So this equality is stronger than this other equality. Okay, so that's basically the result that we can see while again playing around with reverse physics and trying to put all these ideas together. And of course, one of sort of the where does this lead us is that it leads us to this conjecture that I had for a number of years. So suppose that the lower bound on the entropy is the only difference. So we know that is a difference, that classical mechanics does not have, in principle, a lower bound on the entropy of distributions, while quantum mechanics has, right? So that's a difference. Now, suppose that we say that that's the only difference, right? Then it should follow that once we go at high enough entropy, we're very far from the lower bound. Then classical mechanics and quantum mechanics should start looking very similar, because we are far away from the regime in which we clearly have the only difference that we assume. And so for a long time, I had this conjecture that I didn't know how to prove. So last year, I started this channel here. And one of the first videos that I posted, actually the first video that I posted, was this conjecture that is the classical mechanics, the high entropy limit of quantum mechanics. What happened a month and 10 days later is that an atomic physicist from Vienna contacted me and said, "Oh, I saw this video. Have you considered using these techniques?" And so we started chatting. It turns out that he had the complementary background that I needed to actually prove this thing. And in November, we came out with a preprint that actually shows this result. And so this is kind of one of the problems that we have in this project, is that we're trying to combine all these perspectives together from different sides. And of course, not any single person can have competence in all these different areas. For example, I didn't have any competence in quantum mechanics on phase space, Wigner function, QCMQ, and all of that things. He had, and he taught me the things that I needed to do, and I consulted with him and other things, and we were able to write this paper together. So this is kind of why I'm doing this school, why I have this channel. I strongly feel that we have to create some kind of community around these ideas to sort of explore the full power of these approaches. So let me now give you a little bit of an idea of how this works. It becomes very technical, so I'll just give you some sort of a higher level understanding. So what we're essentially looking for is a map that increases the entropy of all mixed states, all the sort of the probability distribution in quantum mechanics. And it does it in a way that a level set of the entropy, so all the mixed states at the same entropy are mapped to a bunch of other states at the same entropy. So we map levels of entropy up and up in terms of all possible states. And what we also want to have that a unitary map between two states here becomes a unitary map here. So if we have a deterministic or reversible evolution between two states, then we apply the map that becomes a deterministic and reversible evolution on the new states, right? And that's what we want to do. We sort of want to take the whole states of mixtures and bring them up to high and high entropy and study what happens there. Now, in classical mechanics, this is very easy to do because as soon as you say, I have a map R that takes a probability distribution, gives me another distribution, and I want this probability distribution to be increased by a constant, what happens is that that constant factor is going to be the logarithm of the Jacobian, and the Jacobian has to be the same over all the transformations. So the only thing that you basically are doing is stretching out phase space. And again, in classical mechanics, this requirement of the map is the same requirement of asking that the Poisson brackets remain, gets this constant in front of it. Now, in quantum mechanics, this is too hard to do. I don't know how to do it. So we take as a definition of a stretching map this idea that we apply the map to two observables and the commutator gets rescaled. And we're going to call a pure stretching map something that essentially takes x and p and stretches them by the square root of the factor, such that when we put them together and put it here, we are going to have a lambda. Now, of course, quantum mechanics is a little more complicated because we have the ordering to take care, things don't commute. And then what you can do is by just assuming that this becomes an infinitesimal transformation, then it has to follow the Lindblad equation. If you know what it is, it's the equation for open quantum system. And then you can find that the jump operator has to be the anti-ladder operator, whatever it's called, and that gamma here, it becomes this lambda, right? So essentially, you can find the transformation that actually takes this thing up, and then find that all the other sort of equivalent transformation are there connected by a unit. So this is complicated to see, but we can see it in a much simpler way that it's in some sense less physical and in some sense more intuitive. So instead of saying I'm going to go up in entropy, I'm going to stay where I am, but I'll take the pure states that live at zero and bring them down. So instead of going up in entropy, I'm going to take the reference and bring it down in entropy. So the entropy difference is going to go to infinity in the same way that it was going there in the real limit. But mathematically, it's a lot easier to understand what's going on. So what's going on if we are increasing the entropy on the transformed, then what happens is that the target is the one that is going to get the factor of lambda. But if we keep the transformed space the same, and we want to start from a space that is at lower entropy, what happens is that the lambda is not going to be here, it's going to be on the original states as an inverse. So you're going to have a lambda here that it's down, and this lambda is going to go to infinity, and will make this commutator go to zero. Or in another way, you're going to say that the h bar over lambda is going to go to zero, or mathematically, you can just say that the h bar goes to zero. And this essentially recovers the group contraction, which is a standard way where mathematicians recover the classical limit. And this works, and it makes both the classical limit of quantum mechanics and the non-relativistic limit of relativistic mechanics look mathematically the same, because it's just a group contraction in both cases. You have some algebra that has a parameter, and you're moving that parameter either to infinity or to zero, however you are going to look at it, and you are changing the form in the state, and in the limit you get classical mechanics in both cases. So for relativistic mechanics, if you go to low speed, it's like mathematically you're taking the speed of light to infinity, not because the speed of light goes to infinity, but your speed is so small that the speed of light looks so big to you, and you might as well say that it's infinite. So in the same way, for quantum mechanics, you are going to be able to say that if we go to high entropy, the entropy and the uncertainty, the related uncertainty of the pure states becomes so small that you might as well say that, again, the uncertainty goes to zero and the entropy goes to minus infinity. Now, what happens here also, this allows us to understand better what the correspondence principle is doing. So Dirac assumes this correspondence principle that you can take Poisson brackets in classical mechanics and put in commutators to get quantum mechanics. And so the idea there, okay, you're doing something mathematically. What is it that you're doing physically? Well, in physically, we saw what's happening. We are looking for a theory that puts a lower bound on the entropy, but recovers classical theory in the limit. And what is a mathematical result? The mathematician tells me it is true, that there is only one way to do it. If you're doing it in phase space, the Moyal bracket, the one used in quantum mechanics for phase space, is the only one parameter group deformation of the Poisson bracket. So if that's if the math corresponds to what we're saying precisely, then we are also saying that there is only one way to do it. There is only one way to quantize the theory, and quantizing a theory in this constant means putting a lower entropy, a lower bound on the entropy, and that's it. There is nothing else, because there is only one way to do the thing that we are actually doing. What is also interesting here is that there is no mechanism for all of this. So in the same way that once you do the classical limit for realistic mechanics, there is no mechanism for which the speeds are low. Like the speed happened to be low for a specific problem, so you can make that approximation. So the same type of reasoning happens here. There is no mechanism for which quantum states become, in a sense, classical. No, you just have to go at high entropy. And once you go at high entropy, if you are at high entropy, for whatever reasons, you are going to get this effect, and you can make this approximation, and you're done. Right. So that's it. So it makes this classical limit very, very nice. So another thing that we see here is that entropy seems to be playing a very important role in both classical mechanics and quantum mechanics. And again, we threaded all these ideas by going back and forth in the spirit of reverse physics, where we are encouraged to go back and forth to understand these things better. But how far can we push this role? Right? Because entropy is always seen as something that applies to statistical mechanics, not something fundamental that it's inside mechanics. So is it that the case? Should you think as entropy as a sort of a derived quantity as we're pushed to typically by learning physics, or there is actually much more a fundamental role that entropy is playing? And so one of the things that we can show, and I actually have a video about it already, is that the geometric structures that we have in classical mechanics are equivalent to exactly the structures that we need in information theory to be able to define entropy and all these related ideas. And there is just a translation in between. And this is kind of the problem that we have right now, that the mathematical structure that we have are sort of completely disconnected from each other, and you can't see that they're actually the same things. If you're doing a geometry in phase space in classical mechanics, you use symplectic manifolds, which is a whole different theory. If you're doing probability, then you're going to use measure theory, and information theory. It's something that sort of takes some ideas from measure, but then you have to be able to have to do some other things, right? So because this is kind of the problem, that the two theory seems to be disconnected. Instead, they're joined at the hip. What happens is that in a symplectic manifold in phase space, so the areas of phase space are defined by what it's called a symplectic form. And the geometry is given by the symplectic form in terms of areas and volumes, and that physically count the number of configuration and number of states. And of course, there is a link between the entropy and the count of states. If I have a uniform distribution over U, then the entropy of that uniform distribution is the logarithm of the count of states. So if I give you the geometric structure and then I have some definition of probability on that structure, I can go and derive the information. I can go and derive the probability, because probability of uniform distribution is 1 over the measure, and the information entropy is just the logarithm of the measure. But it works the other way. If I didn't give you this metric, this symplectic form, and the notion of areas, and just I give you all the distributions and their entropy, since the logarithm is an invertible function, you would be able to go back and forth. You would be able to say, okay, this distribution is uniform around this region. I look at the entropy, I do the exponential, and now I know the area. So you can go back and forth. So either you give me the geometric structure, or you give me the entropic structure, and when you give me one, you exactly given me the other. You gave me no more information. You can go back and forth. And the same happens in quantum mechanics. And in quantum mechanics, we don't have regions and volumes and so on. The geometry is defined by an inner product, and the square root of inner product gives us probability. And if you have two pure states, and you give and you prepare unequal mixtures of those two pure states, and you look at the entropy, then the entropy is a function of the probability of the transition between the two states. And it's not just a function of those, it's an invertible function. So again, you can give me all pair of states and give me their inner product, or you can give me the square of the inner product, or I can give you the entropy for all the equal mixtures of any pairs of states, and from that you can recover the square of the inner product. You can recover the structure that you have on the projective Hilbert space. So this thing that the geometry is entropy works both in classical mechanics and in quantum mechanics. So entropy is really a more fundamental quantity that you think, because it's equivalent to giving these geometric characterization of both classical mechanics and quantum mechanics, which are the structure that you need to define your Hamiltonian evolution. So if this is true, if geometry is entropy in both classical mechanics and quantum mechanics, then it is not true that thermodynamics and statistical mechanics are built on top of mechanics, that you first have to mechanics and then you add some other structure above, because the structure that you gave me, the geometric structure of classical and quantum mechanics, is exactly the thing that I need to define the entropy and everything else. And Hamiltonian mechanics is conservation of entropy, and therefore it's sort of the same thing. So really, we should think of mechanics more as the ideal case of statistical mechanics. It's basically, we're taking all the possible distribution that we have, and since there is linearity in terms of the statistical distribution, if I know that a distribution is made of two distributions, is the sum of two distributions, I can move the components, and I know how to of the whole moves. So if you know how to move around, how to evolve the distribution with the lowest entropy, then you know how to move deterministic and reversible everything else, because everything else is linear. And so the pure states of both classical mechanics and quantum mechanics become that. They are the best state that you can hope to prepare. And in classical mechanics, you assume that you can prepare them with infinite precision. And quantum mechanics is more realistic. It says, no, you can't prepare things with infinite precision, because there is a lower bound on the entropy. And that lower bound on the entropy sets the scale of what you can actually control in terms of the precision of your states. So this is sort of a overview that I hope it gives you the idea of how much nicer, meaningful, and insightful is this way of proceeding. That extracting principle as assumption behind the laws gives you more solid intuition that cuts across all the fields, and it gives you more insights and results. Like we can start being driven by physical ideas much better than just mathematical ones if we have these shortcuts in our brain of the intuition of how to go from one to the other. And again, the way that we do it in reverse physics is to strive to have multiple equivalent starting points. So we can say that we have Hamiltonian mechanics, entropy conservation, and uncertainty conservation. Like all those things turns out in some precise sense to be all equivalent. And this is what we should be doing more, instead of looking at one thing and pretending that everything is that one thing. Have these different perspectives that sort of complement each other. We saw that every detail counts. Somehow dimensional analysis has fallen out of favor, and a lot of new theories that we have are just a bunch of math, and then you fix the units later somehow. But we saw that there is meaning. In fact, another thing that I'm not going to show here, but I did sort of the same work on, let's say, the Dirac equation in quantum field theory of putting the H bars where they need, the C's where they need. And you can understand that equation a lot better once you do that, because now you know what those operations physically means, and you get physical insight. And the other thing is that you should always be open and ready to reinterpret and recombine results. Like this picture that we have right now is the product of an evolution of a bunch of ideas that we tried and said, oh, this works. And then you realize 3 months later that there is something better. And so you always have to be able to take these things from different areas and put them together. And with that, I want to close with sort of a kind of a message that if you are working on foundational questions, you should always have in the back of your mind. Is that you can't really judge arguments you're not familiar with, either yours or others. So many insights that we have had in reverse physics, they basically started as tricks. Like I knew where I wanted to end. I had an idea of where I want to start, and then I start making an argument, right? And these arguments at the beginning, they seemed like completely ridiculous. And it's not, they seem ridiculous because you're not used to making them. And then what happens in some cases that some of them are ridiculous and you throw out, but some others, you think about them more and you find the connections and they become less and less ridiculous as you go through them. And that's kind of the point, is that at the beginning, you are so unfamiliar with our reasoning that you can't see whether there is truth to it. And so that happens to not just the arguments of other people, even yours. And so the point is that a superficial understanding of an argument does not allow you to see the potential connection to other things. And so you sort of have to keep this preposterous argument in your head enough to really see whether it makes sense or not. You're not going to be able to judge it at first. And conversely, there is the other effect. If you are very familiar with a way of reasoning, that way of reasoning is going to prevent you to see the merit of an unfamiliar argument, because your brain paths are always going in the same direction and they're not going through the other direction. So you're not going to be able to see how things work. So the best way to approach that you should have is essentially to remain playful and try things around and see what happens, and never be attached to your ideas. In fact, it's much better if you just say, these are not my ideas, these are just random rocks that I found on the street, and this rock is nice and this other is nice, and if I find another one, I'll just throw it, because they're not my rocks, they're just the things that I found. Okay, so we can now wrap it up. So assumption physics is a different approach to the foundation of physics. We don't have interpretation in the standard sense. We're not going to try to find a theory of everything. We just want the physically meaningful starting points from which we can derive the laws and the mathematical framework they need. And in this setting, physical theories are models. They're not true in some objective sense. They are useful in some cases where the assumptions underneath the models are somewhat verified. And so the goal is to clarify exactly what the realm of applicability of each model is. And what we found, to our surprise, is that most of the time, the realm of applicability of the model is the model. Once you specify these are the conditions in which the models apply, you find the physical theory. So that means that in a physical theory, there is no more than the assumption that you put in. And whether a physical theory applies just means whether your initial assumptions are approximately verified in practice now. So we have this approach called reverse physics, which is whose goal is to reverse engineer the principle from the known laws. And the problem is that the current laws are given through mathematical structure, which make it hard to understand what the physics is. And so we have to find physical principles and assumptions from which we can derive the laws so that we can know what the laws are about. This starting point must have a clear and intuitive meaning for the majority of physicists and engineers. There are a lot of what are called reconstruction of quantum mechanics in the literature. And the problem is that a lot of the time they require mathematical things that you have no idea where they come from. So there is one, for example, that you say, okay, all measurements are probabilities, and then you have states, and somehow the quantities that you need to define the whole sphere are the square of the number of quantities that you can measure at the same time, right? Why? And of course, then people try to justify these things, but it's not something intuitive and clear that physics would have. Instead, if we can say that the difference between classical mechanics and quantum mechanics is just that we have a lower bound on the entropy, well, if you're doing statistical mechanics, which is required anyway when you're doing actual experiment, because you have to sort of think about statistics, you have a clear understanding of what that difference is. It's a lot more intuitive. And so the goal, which of course is not realized, and that's why we needed to build a community of it, would be seeing that all the different results that you would have that are different in classical mechanics and quantum mechanics make sense under the light, and in fact they can be recovered in that sense, in the same way that special relativity is just the fact that the speed of light is invariant, and that is sort of the cause of everything else. And another thing that makes it sort of this approach shows us is that it's very productive to investigate physics as a whole, instead of saying, oh, quantum mechanics is fundamental, therefore I only need to study quantum mechanics and then I'm going to understand everything, or I just need to focus on a theory of everything and then everything is gonna be fine. You're going to lose a lot of insight if you do that. There are, as we said before, some sort of requirement that all physical theories must have, and if you can understand how those relate to each other, then those are going to be there in all theories, and it gives you a much better sense of the physics as a whole than just saying this is the one true thing that is more fundamental. I should only worry about that. So as I said before, this needs to be a collaboration between different things, and the reason why I'm able to do this project is because in the past 10 years I made it a point that I should be able to learn enough about every different single piece of math, physics, computer science, and statistics and whatnot that we need for the project. I need to learn it enough such that I can go to an expert and talk to them in their own language so that I can understand their perspective and try to merge all these things. And of course, I can't be an expert in all of that. And so the only way, as I said, to really make a dent in this problem of setting the foundation of physics on good grounds is to be able to create a community around it. And I have no idea how to do it because it's very interdisciplinary, and the academia really works in little fields that don't quite talk to each other. And so I decided that from the beginning to basically make this an open source project in the style that you have in software engineering, because that's the practice. So our main output of the project is an open access book, which is available through our website, but it's also available on GitHub. And sometimes I get a pull request because somebody made some fixes of typos. So they're the things that make me very happy. So if you want to make me happy, do those type of things. We have one YouTube channel dedicated to publicize, which you probably know, where we put sort of results, but we also have another one where we do the research, where we are trying to do live stream discussion, and I would hope that more people sort of come and participate to these things. We also have a Discord server, so if you're interested in these type of things, just contact me and I will give you an invite. I'm trying to keep it a space where people are interested in discussing real details and not like weird theories that sort of don't even match with the purpose of the project. We want to be extremely focused because we already have so few resources that I can't stay there and the news about the interpretation of quantum mechanics that are not strictly in the scope, and so like that's what I'm trying to do, and so far we have been successful, and so on. And so then I'm always looking for experts to get insight and help. I'm looking always for people to collaborate, and even people in academia that can suggest me which journal and conferences could be sympathetic to this, because again, it's not very easy to do. And to learn more, as we said, we have a project website, their YouTube channel, and our GitHub repository. And I think that's all for this session, so we can open it to questions. Christine, tell me what questions are there.
All right. Yeah, we already have a few questions in the Q&A. So the first one from Carlos is, when you say the classical uncertainty principle is h bar over E, quantum one is h bar over 2, so the classical one is less than the quantum one. You're identifying the classical area H with the Planck constant. What is the reason for such an identification?
So the identification comes because so even in quantum mechanics, h bar is a constant that you go and measure, right? And you measure it because you're going to have some, you can go and measure in this case, we can go and measure the entropy, right, of a classical ideal gas at high temperature. And that entropy is going to have to match with the prediction of the theory, right? And so since these two curves are going to coincide, because they have to coincide, because they have to coincide to the experimental data, what's going to happen is these two h bar are going to coincide. Now, the difference in number here basically is telling you that you can squeeze a little bit more precision in classical mechanics than in quantum mechanics, right? And there is a justification, at least intuitive. I like to make it precise. I don't know how to make it precise, so if somebody wants to help me make it precise, it would be great. But this is the intuition, is in classical mechanics, you get this lower limit on the uncertainty, not just because you have a Gaussian, but because the two Gaussians in position and momentum are independent. So you have the full Gaussian is the product of the two Gaussians, right? And you can do that because Q and P are independent variables, and so the preparation of one does not affect the preparation of the other. In quantum mechanics, position and momentum are not independent variables in that sense, because any preparation of Q influences the preparation of P. So this lack of independence means that you're not going to be able to have that the joint distribution is the product of the two marginals, like you have in classical mechanics. And therefore, you are going to have something where the bounds on the entropy, on the uncertainty is a little bit higher than you would have in classical mechanics. So again, there are physical reasons of why these things work and make sense. So I hope it made sense.
Okay. Next question we have is from Thomas. The uncertainty principle in quantum mechanics is usually explained in terms of wave mechanics. How does the entropic uncertainty and the wave uncertainty relate?
I do not know. So what I do not know is why if I put this entropy constraint between position and momentum, they become the fact that the one distribution is the Fourier transform of the other. Like I don't see that step. What I know that even in classical mechanics, if you have sort of a distribution of one variable and you make the Fourier transform, so it's all real numbers, you are going to get an uncertainty principle of that type. But the issue is that in classical mechanics on phase space, Q and P are two different independent variables. So there is no connection between one being the Fourier transform of the other. So I would like if there were an argument that said, well, once you make this bound, then you're going to get the wave mechanics somehow. I don't know how to do it. I don't see it.
Okay, somewhat related, mentioning Fourier transforms.
Wait, like if there are comments on the chat, so I'll there's a follow up on the chat on this. So the classical uncertainty follows the underlying symplectic structure of phase space, the Brownian non-quadratic. Exactly. That's kind of why you have it. And the symplectic structure, as I said, is the thing that gives you the entropy. So those two things are related. I do not know, and maybe they exist in the literature. I personally do not know how these structures would relate to wave mechanics. Like I can sort of see that if we say that the position actually becomes a velocity, and we kind of have a field theory, right? Then this velocity becomes a wave propagation and so on. I might be able to see how this works, but I don't see the details. And in all these things, I'm always I much rather say I have no idea when I don't know the details, even if I'm 90% there, because a lot of the time the extra 10% screws everything up. So I don't want to commit to saying that something, I don't know how something works if I'm not sure that the last 10%. The action becomes the phase in the wave. Again, maybe, I don't know. The action, we'll see it in the next section. I have a geometrical interpretation of the action, and maybe there is a way to link that with wave mechanics. I don't know.
Okay,
next question.
Yep, moving on to the next question from Daryl. My intuition of the uncertainty principle is from noting that position and momentum are Fourier transform variables. If we see two blinking lights with similar frequency for long enough, we can tell the frequencies apart, but we cannot localize it well in time. Yes. How does this relate to the entropic uncertainty you presented?
Right, so in quantum mechanics, it's the same thing. It's a different thing. And I do not know how the two are related. I strongly feel that there should be a relation, because it would be very intuitive that, you know, it would make sense that there was, but I don't know. My knowledge is limited, so that's why somebody else can work on this, and maybe we can work. We could have an in-depth discussion of this if anybody wants in a live, in which we try to take all these pieces and put it on the table and see if there is anything that fits together. That would be fun.
Want to go back to the chat. I think there's another follow-up from the previous, like in the WKB approximation. I think this is going back.
So I do not know how the WKB approximation relates to sort of the high entropy limit. So I do not know if that approximation is something else completely or not. I'm not I'm not too far. Like, I haven't looked in the WKB approximation in the last time it was probably going to be 15 years ago. So I don't know how it would fit in all of this. And again, it's exactly some pieces where somebody can say, okay, I'll have a look at this. So as I said, like I'm describing sort of the approach. To me is more important than the result. And so applying the same approach to these other questions, it's something that I'd like to have other people help me. I just had an email, for example, 2 weeks ago for somebody that has looked at the interpretation of the action principle, and he was interested in trying to extend it to the case where you do have dissipative forces, which I thought that it was impossible. And then we discussed a little bit, and actually that there seems to be a way that connects to other things, and then it connects to other things that I'm looking in quantum mechanics, actually. But these are exactly the type of things that I'm looking, like people that then are going to say, okay, let's go and look how these things work.
Okay. Another question from Daryl. Do you see assumptions of physics as laying the groundwork so that it is easier to form new models, such as a theory of quantum gravity?
Yes. I don't think we are going to have quantum gravity until we figure out exactly what are the assumptions that we have in general relativity, the assumption that we have in quantum field theory, understand why is it that they are incompatible, like conceptually, whether the math that we have, make the math that we need for those two theories precise, because I'm not even sure that we are there yet. And then you need to be, because you're going to be able to say, okay, these assumptions are no longer valid. I need to put other assumptions to be able to build the quantum gravity, because I'm going to be in a different regime. I don't even have a sense that the mathematical structure that we currently have right now are going to be working in the assumption and the regimes that we want a theory of quantum gravity work. So it could be that the current math that we have works fine, and you just need to know how. Or it could be that it's totally wrong and we need some different type of math. I don't have the tools to make that evaluation complete right now, because I do not know exactly what are the assumptions built in all these things, because there are some technical problems that I have no idea how to solve. But from the hints that we have, and that we're going to see when we talk about in the open problems, like my hunch is that we don't have the correct structure. So it's one of those. So the problem is that when quantum gravity is going to be a sort of a generalization in some sense of the two theories that we have, and what you can do without understanding things well, you can do interpolation. So if you have two theories and you know that you have a theory that it's in between, you can say, I can make a prediction to that. But if I have these theories, the realm of applicability, this probability, and you have to work here, this extrapolation like that, I don't think it's going to work. So answer is, for me, is a strong yes.
Actually, before I forget, let me come to a practical question that was sent privately to the hosts. So if people do want to contact you to be added to the Discord server, how would you prefer to be contacted? So the info@assumptionsopphysics.org, or your university address, or something else?
Either. They just come to me anyway.
Okay. Okay, so yeah, for example, well, yeah, the Assumptions of Physics website has the email for the project listed at the bottom of the page, which is info@assumptionsopphysics.org. And it's also easy
And
to.
my email is there in any paper that I wrote, so it's
Yes,
I'm not very hard to find. Also, I have the blessing of the curse of essentially being the only person with my name and last name. So if you search me over the internet, you find me.
Okay. So going back to the Q&A, can you explain again how you recover the classical regime from quantum mechanics in the regime of high entropy?
Okay. So I would need a lot more time to do it, but the basic idea is this. So and I don't know how much physics you know. So in quantum mechanics, you have pure states, which are your typical wave function. Then you have mixed states, which are the density matrices. They are essentially statistical distribution of that, right? And so if we're looking at this plot where we are essentially looking at the uncertainty of each mixed state and the entropy of each mixed state, you can imagine that each of these points, we have a bunch of mixed state, because there are going to be a lot of mixed state at the same uncertainty with the same entropy. So what you want to do to basically say, I want to make the high entropy limit, you want to make, so let me do this first. That it's very annoying. There you go. There is the pointer that keeps disappearing. Okay, so you want to basically look at what happens at a high entropy. And the way that you go and look at it, you make a transformation that takes states and bring them up and up and up, and you study what happens when you're making that change. You have a couple of ways to do it. What we're doing in the paper is to look at what happens at the Wigner function, for example, or the Husimi function. Now, Wigner function is, maybe you heard it, it's this idea that you have negative probabilities. You have this quasi-probability distribution in phase space that are functions that integrate to one. but there are zones that have negative probability. And there are multiple ways to represent mixed states in quantum states with this type of quasi-probability distribution. The Wigner functions have the nice property that if you make an expectation of position and momentum on this phase space using the Wigner functions, then you are going to get the expectation of the polynomials of position and momentum that are in symmetric order. So you basically take all the permutation of position and momentum, you average them out, and now the expectation of that is going to be the classical expectation using the quasi-probability distribution. So the typical way that you do the classical limit is by looking at what happens at the Wigner functions and at the Moyal bracket. The Moyal bracket is essentially the corresponding of the Poisson bracket in quantum mechanics and phase space, which is also the correspondence of the commutator in quantum mechanics and phase space. And what happens is that the Moyal bracket will have an h bar as a parameter. And if you take that limit of h bar that goes to 0, the first term, the one that remains, is the Poisson bracket, and all the other things are correction terms of that h bar. And so mathematically, you have Moyal bracket equal Poisson bracket plus terms in h bar. You make the h bar that goes to 0, those terms disappear, and now you have recovered classical mechanics, right? That's basically how you get the classical limit. What we want to show is that when you're making these steps that you're going to go to higher and higher entropy, we are keeping h bar fixed, but these terms that will go to 0 as you take h bar goes to 0 are also going to go to 0 when you make this stretching go to infinity, when you make the entropy, this transformation become more and more. So you're going to have some kind of stretching coefficient gamma that tells you how high in entropy you're going to go. The Moyal bracket is going to be Poisson bracket plus these terms with this gamma, and then you're going to go into share, as this gamma goes to infinity, these terms are going to disappear in the same way that they would disappear if you made h bar go to 0. That's basically how it works technically. And so what we need to find is what we found in the paper. We found an example of a transformation that does this. We check that make all the entropy go up. We checked a bunch of the different things, and then you say, okay, instead of thinking of h bar going to 0, we can think it as we are making this stretching, this higher and higher, going to higher and higher entropy. What happens to the Wigner function is that the Wigner function gets stretched in position and momentum, like you would expect, because you are basically, to increase the entropy, we're stretching position and momentum and making these distributions more and more spread. But it doesn't only get stretched, it gets also convolved with a Gaussian, meaning that the areas of negative entropy, they do remain small, and in the limit, they actually become positive, or they become non-negative. And this is because there is another function, quasi-probability distribution, which is called the Husimi Q distribution, which has the property, instead of giving you these products in these symmetric orders, there are other orders, the normal order, then the anti-normal order, that are in terms of the ladder operators of the what's it called, of the harmonic oscillator. And as I said before, the anti-normal order is the one in which you get the nice commutation relationship. And so the Husimi Q is the one that sort of sees this transformation. But the only thing that it sees is the position and momentum get stretched. Now, the Husimi Q has this interesting property that it's still a quasi-probability distribution, but it's non-negative. There are no negative areas. is still a quasi-probability distribution because the points are not independent event like you would have in classical mechanics. That if you prepare one, you kind of have to prepare another one anyway. So what happens to the UCMQ is just that it gets stretched. So it's always positive, and it just gets stretched. And in the limit, the Wigner function becomes closer and closer to the UCMQ. So you have guaranteed that the Wigner function becomes less and less non-negative, because in the limit it's going to become always non-negative. And the expectation that you would have on the OCMQ becomes the same as the expectations that you would have in the Wigner functions, which means that if you make now the expectation in symmetric order or antinormal order, it becomes the same. So the ordering of the operator doesn't matter anymore, and that tells you, okay, then the position momenta are going to be commuted. So there are all these nice insights that sort of all work together, and you know, it would be a lecture in itself. So I hope that at least this gives you a better idea of how it works at the technical level.
Moving on to the next question from Isaiah. Are you assuming that the universe can be neatly divided into regimes, classical, quantum, classical, etc.? Can these models be applied to intermediate regions, say between classical and quantum?
Right. So the assumptions are strict. The universe is not, right? So you could make the case that both the classical assumption and the quantum assumptions are like even the idea that you have these system that you can completely isolate them, right? It's of course it's an assumption. It's never going to work. And the thing that at a physical level I'm not so clear is whether these assumptions that are essentially simplification assumptions, right? Because you say, for example, I have a Hamiltonian evolution means complete isolation. It's never going to work. It doesn't exist, but in a lot of places it works. If I have quantum states, for example, I can study a proton or an atom as a single quantum state, as a single wave function packet. And I can only do that if I assume that the internal dynamics doesn't matter, and if all the processes that I'm studying do not elicit the internal dynamics, it doesn't matter. So the atom can be studied as a whole, the proton can be studied as a whole. But then, of course, these are idealization as well. Like there are definitely regimes in which you can't study a proton or an atom as a single object, a single quantum object. It's going to be a composite object. Quite frankly, is an electron a composite object? Is it an assumption that it's in a composite object? I don't know, right? We assume it because in all the processes that we've studied, that's a valid assumption. Whether it's a real assumption, we don't know. And so the universe, it's what it is. It's a complete mess. And then we find some, systems that in some cases we can model with these assumptions. Some systems seems to be, following the assumption better than others, but we can't guarantee that the assumption is always going to be valid. We cannot guarantee that electron do not have a substructure and therefore they're always be described as a single quantum object. I cannot guarantee that during an emission process, where a scattering process, when an electron emits a photon or stuff like that, there is no intermediate things where you don't really have an electron, don't really have a photon, but you have something in between. I have no idea. Maybe we're gonna, maybe for quantum gravity, we will need to have some of that description. I have no idea. So what I know is that there is a universe. There are some models that I make under simplifying assumption. To me, the open question is whether the assumptions are actually needed to be able to create the theory. So it could be that since I want to make my theory rigorous and with math and funny symbols and all precise, it could be that at some point I have to make a cut. I have to make a cut that says these are the things that are in the theory, and it has to be a sharp cut because the theory has to be mathematically precise. So it could be that there is no way of doing this without making this assumption that in some sense simplify and in some sense also make sharp the division, for example, between system and environment. Can we define, whenever we're taking a system, we have to define, okay, this is part of the system and this is part of the environment. Otherwise, how can I define a notion of a state? But you could argue that that thing doesn't exist. Like in the universe, there is no such thing as this sharp division. And then you would be arguing that all the physical models that we're doing are always going to be some approximation, because in the process of describing and writing a formal physical theory, we have to make that assumption. So that's the part that, for our philosophers that are interested in that question, and we can make an argument to that all physical theory needs to have this assumption, these assumptions that are always simplificatory assumptions, that would be interesting to me. So I don't know if this answers the question, but these are the thoughts that I personally have in my head.
I can just point out related to that. I mean, just looking at recovering classical mechanics as the high entropy limit of quantum mechanics, then this also implies that you have these intermediate regimes where you, just like in the case of relativistic classical mechanics versus non-relativistic, you can use the non-relativistic equations if you're at 10% or 5% of the speed of light or something, and you can calculate quantitatively exactly how much you're going to be off from the more detailed calculation using relativistic mechanics, and you could calculate at low but not super low entropy using classical equations and quantify how much you'll be off by not using the quantum ones. So this would treat intermediate regions between classical and quantum. The last question in the chat by Arnav. As far as I understand, you say that classical mechanics and thermodynamics are equivalent formulations. How do you incorporate knowledge of the observer in classical mechanics? Isn't thermodynamics a richer theory in that sense? I can see that this can be done for quantum using density operators, but how do you handle this in classical mechanics? And Artem has a few comments, another participant. I can read the comments from another participant related to this question. You can incorporate knowledge of the observer by working with probability distributions on phase space, the usual stuff that you do in StatMech. The great insight is that before going to probability distributions, the symplectic structure already defines entropy.
Right. So let me see. That's to have I can actually see the question. I can just open it up.
So relating classical and thermodynamics, and how do you incorporate knowledge of the observer in classical mechanics?
Okay, so this basically relates to the question of what the actual entropy is described. And this is a whole different kind of work, because there are two ways that entropy is described in statistical mechanics. One is this Bayesian way of saying it's the lack of knowledge of the observer, and it has some problems. And then there is the other one that is instead characterizing the fluctuations of the system with respect to external interaction. So something is, when you take something and you put it and it increases the entropy and therefore increases the temperature and therefore increases the entropy, it's not that you are, it's the same as, oh, I don't know what's happening, I'm less clueful. Is that the external interaction is increasing the number of ways that the system can fluctuate. And there are theorems in statistical mechanics that relates the number of fluctuation to the entropy. And there are when people do thermodynamics out of equilibrium, a lot of the time they actually use the entropy to characterize the fluctuation, and in some sense they're measuring the entropy by looking at the fluctuation. And again, also that can be understood in terms of sort of information ideas, because there is something that is making these fluctuations, and the fluctuation comes from the outside, so you don't know what's going to happen. And so the information that is lost due to the outside fluctuation can still be used to characterize the entropy. So there is this whole kind of worm, and I try when I develop these ideas to be as general as possible so that I can keep some of these ideas outside of this kind of world. And so the way that you do it, that it's similar for both classical mechanics and quantum mechanics, you can relate essentially the probability distribution is characterized, as long as your probability distribution goes down at infinity like an exponential, it's a Schwartz function, you can relate that probability distribution with the expectation of all polynomial of position and momentum. So the way that you say, you could say, I have a probability distribution over phase space, or you could say, I have a way to prepare a system that has all these expectations well defined. So in that sense, you can sort of go back and forth, and then there is no knowledge, because in that sense, what you do in terms of expectation is the same as if it's a Bayesian lack of knowledge or if it's external interaction. And so you can run the argument of sort of the connection between the symplectic form and the entropic structure with both arguments. You can say, I can imagine that my entropy is a Bayesian type of entropy because it's lack of knowledge, or it's because it's an internal system that it's making my system fluctuate. And in fact, the probability distribution is the exploration of my state in a given delta t that it's given by the time scale of the definition of my microstate. And fortunately, things work out in the same way. And so you can now be a Bayesian and use my argument, or hate Bayesian and still use my argument.
Okay, that also answers the follow-up question in the chat from Artem. It's 11:30 Michigan time.
Yeah, exactly. This is exactly what Artem said. Yes, I need maybe like 1 minute so that I can disappear for 1 second, and I'll be right back.